Okay, so in the last class we saw that this dx is equal to f times dx, and then because f is invertible, we can also write it as the d capital X is f inverse times d small x. So we'll use these relations now to define a strain measure. So first we will define a Lagrangian strain measure, which is known as the green strain tensor. So if I now write ds square minus ds square, so let us draw the undeformed configuration, and then your ds is some element of length in the undeformed configuration, and it goes into some deformed configuration. Now imagine that this curve is going to this deformed curve now, and this ds is now getting mapped to this d of s, small s. Okay, so the change in length, we can express it in this following manner: ds square minus ds square is equal to dx dot dx minus dx dot dx. And this we can write as equal to dx dot f transpose f minus identity times dx. So here I am substituting for small dx. So I am writing first this as f times d capital X, and this also I am writing as f times capital Dx. Then I am using the definition of the transpose of a tensor, so I can write it in this particular way. So this can be written as equal to dx dot c minus I times dx, and this in turn I will write as dx dot e times dx. So this C is known as the right Cauchy-Green strain tensor. So this C is equal to F transpose F. So I will put a colon equal to, so that means we are defining this object, and this is known as the right Cauchy-Green strain tensor. And this E here, which is half of C minus I, that is known as the green strain tensor. Is known as the green strain tensor. And because it is in terms of capital X, so hence it's a Lagrangian measure of strain. So this is a Lagrangian measure of strain. Yes. So in initial notation, I can write this as, so let me write it here. So Eij is equal to half of del chi k by del xi del chi k by del xj minus delta ij. So this is the initial notation version of this particular relation here. So this is half of c minus I. Now this factor half is actually, from a mathematical viewpoint, we don't need this factor half, but basically, historically speaking, the small strain tensor came first, and then this nonlinear Lagrangian strain was defined at a later stage. So in order that the approximation, the linear approximation of this Lagrangian strain tensor agree with the linear strain tensor, which was historically speaking defined earlier, we put this half factor. So as I said, not strictly required from a mathematical viewpoint, but in order that it agree with the linear strain tensor to a first approximation, we put this factor half in there. Okay, then now just like we defined the Lagrangian measure of strain, now let us define the Eulerian measure of strain. So again we start with ds square minus ds square, so that is equal to dx dot dx minus dx capital X dot d capital X, and then this is equal to dx dot. So now I will express this dx in terms of small dx using this F inverse relation here. So I can now again use the definition of the transpose, and I can write this as F inverse transpose F inverse times d small x. Okay, so, and this I can write as equal to dx dot I minus d inverse times dx, and this in turn I write as dx dot E bar times d small x. So this b now, which is equal to half of b is equal to ff transpose. So b is equal to ff transpose. This is known as the left Cauchy-Green strain tensor. Left Cauchy-Green strain tensor. And this E bar is equal to, so this E bar is half of I minus B inverse. I minus B inverse, which is also equal to half of I minus F inverse transpose F inverse. So this is known as the Almanzi strain tensor. This E bar is known as the Almanzi strain tensor, and it's a Eulerian measure of strain, because last time we have seen that F inverse can be expressed as a derivative, partial derivative with respect to the small x, which is the spatial position. And so you can see that this is involving derivatives with respect to small x, and hence you can say that this is an Eulerian measure of strain because of that, because it is expressed in terms of the spatial coordinates. So this is an Eulerian measure of strain. Alright, so we can see some of the symmetries that are inherent in all these tensors. So obviously B is symmetric, C is symmetric, E is symmetric, and E bar is also symmetric. So all of these tensors are symmetric. So we can write that. So C, B, E bar, they all belong to symmetry. So all of them are symmetric, and then you can always use the polar decomposition to decompose F as Ru and also equal to Br. So let us write that decomposition also for this case. Yeah. So let us write that. So C, and so F is equal to R times U, which is equal to V times R. So we use the polar decomposition now applied to the deformation gradient in this particular case, and so we will have that C is equal to F transpose F, that is equal to U square, and B is equal to FF transpose, that is equal to V square. And we also have the relation that C now is equal to U times U, that is equal to R transpose. So from this we can get, so from this particular relation we have that U is R transpose VR, correct? And so if you just substitute that here, so R transpose VR times R transpose VR, so that will give us R transpose times V square times R, which is equal to R transpose times B times R. So the tensors C and B are orthogonally equivalent. Okay, so that means they have the same eigenvalues. C and B have the same eigenvalues. Okay, and the relation between E and E bar, so we have seen that E is equal to half of F transpose F minus identity, and we have seen that this E bar is half of I minus F inverse transpose times F inverse. So you can find a relation between E and E bar. So this relation is E is equal to F transpose times E bar times F. And we can also see that actually because F is an invertible tensor, so hence we can say that C and D also belong to P sim. That means they are symmetric and positive definite tensors because F is invertible. So you can easily show that they are not just symmetric, but they are positive definite as well. So C and D also belong to P sim here. Okay, so fine. So how do we write the Lagrangian measure of strain in terms of the displacement gradient now? So let's see that. So we have the relation that F is equal to I plus del U, del of U, and so we can write now the relation for E in terms of the displacement gradient. I can write it as F transpose F minus identity is equal to half of del U plus del U transpose plus del U transpose times del U. So I can write it in terms of the displacement gradient in this particular way. And then you can see now that there are these nonlinear terms now in the strain tensors, in the strain displacement relation. So as an approximation now, if you drop this particular term, okay, suppose if so let me just define the linear strain tensor also, since we are at this particular point. So if now your del Ui by del xj, right, the norm is much smaller than 1 for I equal to 1 to 3 and j equal to 1 to 3, then we can drop this particular term. And then, so remember that we can say that this is much smaller than 1 because this is a non-dimensional quantity, right? U has units of length, that is meters, let us say, and then capital X also has units of length, which is meters, and then this is a non-dimensional number. So all of these 9 non-dimensional quantities in terms of magnitude should be much smaller than 1. So let us say of the order of 10 to the minus 2 or something like that. So then the quadratic terms will be of the order of 10 raised to minus 4, let us say, and then so the 10 raised to minus 4 can be then neglected in comparison to the 10 raised to minus 2, let us say. So of course 10 raised to minus 2 is just a rough number. So that depends on the particular situation. I mean, but it has to be much smaller than 1. Let us just put it in that particular way. And then you can make the approximation that the nonlinear terms can be dropped in that particular case, and then you can define the linear strain tensor here. So the linear epsilon is equal to half of del U plus del U transpose. So this would be the linearized strain tensor. Linearized strain tensor. Yes. Fine. So, but the important thing to remember here is that for the nonlinear strain also, see, we are having terms only up to quadratic, but you have to remember that this is an exact strain relation. So it is not that it is like some infinite series and then we have truncated this infinite series at the quadratic terms. It is not like that. This is actually the exact strain measure. So it goes only up to quadratic. I mean, there are no higher order terms in this particular expression. So that of course is because we have taken the length, right, ds square minus ds square for defining it. So obviously that is the reason that you get only up to the quadratic terms here, right? Because our length measure is based on this ds square. Fine. So now let us look at some physical interpretation of this strain tensor here. But before doing that, let me just give you one expression here. So just like we defined this E in terms of the displacement gradient, it is also possible to define E bar also in terms of the displacement gradient. So let me just write that expression also. Minus del x u transpose times del x u. So this gradient now is with respect to the spatial position, small x, not with respect to the capital X. And note that there is a minus sign. Here there was a plus sign, here there is a minus sign. So this would be the Eulerian strain measure, the Almanzi strain in terms of the displacement gradient. But again, as I said, that here the displacement gradient is with respect to the material position, that is capital X. Here the displacement gradient is with respect to the spatial position vector, that is small x. So that difference you have to keep in mind. Okay, so now we can go to the physical interpretation of this E. See, so actually for the nonlinear strain measure, it is difficult to give a physical interpretation for each component. For the linear strain measure, we sort of know the physical interpretation, that the normal strains are change in length per unit length. You can give it that interpretation, and then the shear strain components, you can give the interpretation that it is a change in angle, let us say, right? So suppose if you have like a block and then you are shearing it, then this change in angle you can relate to the shear strain component. So it is somewhat easy to give physical interpretation to the linearized strain tensor, but to give a similar interpretation for the nonlinear strain is not so trivial. So instead of that, what we do is that we will give a very good physical interpretation for the entire strain tensor. Okay, so what we will show is that the vanishing of the strain tensor is linked to rigid motion. Okay, so what we are going to show is that basically any valid strain measure, whether it is E or E bar or any, so in fact there are an infinite number of strain measures. So here we have defined only E and E bar, but similarly you can define an infinite number of strain measures. So any valid strain measure basically vanishes if the motion is rigid, and if the strain vanishes, then the motion is rigid. And if the motion is rigid, then the strain vanishes. So it's an if and only if statement here, and so that is what we are now going to show, that if the motion is rigid, then E is equal to 0, and if E is equal to 0, then the motion is rigid. So first, before that, let us first define what we mean by a rigid motion. So motion is said to be rigid if it preserves distances between any two points at all times. So that means your x1 minus x2 dot x1 minus x2 is equal to x1 minus x2 dot x1 minus x2. So that means, suppose if you had your x1, x2, now the body is just this x1, x2 is now this x1 is going to this x1, this x2 is going to this x2 here, and then the distance between these any two points. So here I have just considered these 2 points, but any 2 points, that distance should be preserved. Okay, and then then it is said to be a rigid motion for all x1, x2 belonging to V, and for all G 0. Yes, so I can write this also in another form. So I can also write this as chi of x1 comma t minus chi of x2 comma t dot chi of x1 comma t minus chi of x2 comma t is equal to x1 minus x2 dot x1 minus x2. So you can also write it in terms of the chi map, because x1 is equal to chi of x1 comma t and x2 is chi of x2 comma t. So now in terms of this rigid motion, let us give a characterization. So let me call this particular relation as star. Okay, so this is what characterizes rigid motion. So theorem now, characterization of rigid motion. So I am writing this 1 because this is the first characterization that I am going to give you. Later on, I will also give you a characterization in terms of velocity gradients. Okay, so we have not yet introduced the concept of velocity, acceleration, and so on. So at a later stage, when we introduce that, we will give another characterization, which is in terms of this of the velocity gradient. So at this stage, let us just give the characterization in terms of the strain, the Lagrangian strain measure. So TFAE. So that means the following are equivalent. That is the terminology that we are using. A is the motion is rigid. Motion is rigid. So that means the star holds. And 2B, or let me just write this as 1. Then this, let me write this as 2, is that the motion is of the form chi of x comma t is q of t times capital X plus z of t. Way. And this Q is a proper orthogonal tensor. So Q of T belongs to R plus. And this C of T is just a vector. Yes. So physically, basically this corresponds to a translation and a rotation. So you can think of, so suppose if you take this duster, right? So if you translate it and if you rotate it, right, then you can easily see that the distance between any 2 points, right, is preserved. So you can see that. So if I mark 2 points on this duster here, and then now you can see that as I move the duster, right, there is a translation and also the rotation, and then the distance between any 2 points on this duster is preserved. So those are the 2 statements that I have written. And then we can link it to the strain tensor also. So that is the third statement now. That is E of x comma t is equal to 0. E of x comma t is equal to 0. Or alternatively, that is C is equal to the identity tensor. Because E is half of C minus I. So if E is equal to 0, then C is equal to identity tensor. So these are the 3 statements, and we are saying that basically these are all equivalent. So that means 1 implies 2, 2 implies 1, 2 implies 3, 3 implies 2, and so on. Okay, so the way we will prove it is that we will show that 1 implies 2, 2 implies 3, and 3 implies 1. So that is what we are going to show now. So, proof now. So, 1 implies 2, implies 3, implies 1. So, this is what we are going to show. So, okay. So, first let us show that 1 implies 2. So that means star holds, right? So first we will show that 1 implies 2. So since star holds, so differentiating star, right? With respect to x1, x2, with respect to x2. We'll get f of x2 comma t transpose times chi of x1 comma t minus chi of x2 comma t is equal to x1 minus x2. Okay, so the way we got this particular statement by differentiating this with respect to x2, this is just an exercise in indicial notation, and so you can easily try it. Okay, so just write this as ai bi. So suppose if this is this whole vector, you call it as a, and this is another a. So this is ai, and then this, suppose if you take it as b, then write this as bi, and then use indicial notation and so on to get this particular result. So that I am not going to show because that is just a sort of easy exercise using indicial notation. Yes, then now if you differentiate this relation with respect to x1, then what happens? So let us see that. This is yes. Now differentiate with respect to x1. Okay, then what we'll get is that f of x2 comma t transpose times f of x1 comma t is equal to identity. Okay, because once you differentiate this with respect to x1, then you will get the identity tensor here. Fine. Now this is valid for all x1, x2 belonging to V0. So V0 is the material volume in the undeformed configuration here. Okay, so now since it is valid for all x1, x2, we can set x2 to be x1. Okay, so set x2, so I'll take x2 to be equal to x1. Okay, then in that case, what we'll get, this is x2 here. So in that case, what we'll get is that f of x1 now, x1 comma t transpose times f of x1 comma t is equal to identity. But that means that it is orthogonal, right? So this implies that f of x comma t belongs to orth plus, because the determinant is always greater than 0, and so once we say that it is orthogonal, it also has to be proper orthogonal, right? So this is f of x comma t belongs to orth plus. Okay, and then so what I can do is that I can multiply this by, so now if I go back to this particular relation now, so let me just write this as 1. Okay, if I now multiply 1 by f at x1 comma t transpose, or let me multiply it from this side by f of x2 comma t. Okay, so multiply. So here you multiply this by f at x2 comma t. Okay? And because it is orthogonal, then ff transpose is identity. So what I will get is that, so from this particular relation now, what I will get is f of x1 comma t is equal to f of x2 comma t. Right? And hence, what we have shown is that it is independent of capital X, and hence it's a function of time alone. So this implies that f is equal to f of t, okay, and that belongs to all plus. And so let us call this as q. So let us call this as equal to some q of t instead of f of t. Let us just call it as q of t, and then f is nothing but del of chi. Okay, and now you just integrate this particular relation, and then the c of t that was there in the statement, that is just like an integration constant. You can think about it. So this chi now of x comma t is equal to q of t times x plus c of t. So this you can think of as an integration constant. Of course, it's a vector real quantity because you are integrating a tensorial equation in this particular case here. So okay, so what we have now shown is that 1 implies 2. Correct? So now let us show that 2 implies 3 now. So let's go back here. Yes, so now we will show that 2 implies 3. So 2 implies 3. That is what we want to show. So now we are given that chi of x comma t is equal to q of t times x plus c of t. So now if you take the gradient of this, so this implies that f is equal to del of chi is equal to q of t belongs to all plus. Correct? So and then from this it will directly follow that c is equal to f transpose f is equal to q transpose q is equal to identity, and so this implies that E is equal to half of c minus I is equal to 0. So you get that the Lagrangian measure of strain vanishes. Okay, so that shows 2 implies 3. Now we want to show that 3 implies 1. Okay, so that is now the last step in this particular proof here. So 3 implies 1. So what we want to show is that now E is given to be 0, and we want to show that the motion is rigid. So that means that star, whatever I have just erased, that that the distance between any 2 points is preserved. That relation we want to now show from the fact that E is equal to 0. So now given, right, now you are given that E is equal to 0. Right, so let us write this here. Yes. So we have seen now that if E is equal to 0, then this will imply that ds square is equal to ds square, right? Because if we saw that ds square minus ds square is 2 times E times 2 times dx dot E d capital Dx. So if E is equal to 0, then you will get ds square equal to ds. Correct? So this is ds is equal to dx itself, right? So so from this, what you will get is that suppose if you now take some curve, right, in the undeformed configuration, and let us call this as your ds. Right? Now if you integrate it along this particular curve, now what you are saying is now your ds is equal to this ds, and so if you integrate it, then the length of any curve, right, is going to remain the same because you are integrating it across. I mean, each element is now the same, and so the length of any curve in the undeformed and in the deformed configurations is going to be the same because of this particular thing. So what we do now is that we consider in a straight line joining 2 points here. Okay, so let us take a straight line that is joining 2 points here, x1 and x2. Okay, and now you imagine that it goes into the deformed configuration where, so it goes into, let us say, a curve here. So this is your x1 and this is your x2. So what we have said is that now the length of this curve and the length of this curve is going to remain the same. Okay, so this, if I call this length as L, then this length along this particular curve is also going to be L. Okay, so so what we can see from this is that L is equal to x1 minus x2, so that is just the distance between these 2 points. That is going to be greater than or equal to x1 minus x2. So because the because it has gone into a curve, this L is always going to be greater than equal to the distance between these 2 points x1 and x2, right? But we have to write it as greater than or equal to, because it is also possible that this straight line has gone into a straight line also. So we do not know whether it, but so in general we assume that it is some curve which could also be this straight line. So if it is a curve, then it will be strictly greater than, but if it has gone into the straight line, then it can also be equal to. So we write it as it can be greater than or equal to. We do not know at this particular stage whether it is greater than or equal to, or it can be both at this particular stage. Okay, then similarly, so what we have shown is that this x1 minus x2 is greater than or equal to this x1 minus x2. Now, take the other scenario where now you take a curve that is connecting this x1 and x2, and now it goes into a straight line here. So x1 and x2. Okay. So basically now we start with the deformed configuration and consider a line in the deformed configuration, and then backtrack and find out what is the curve that has gone into this straight line here. And suppose if this is the curve now suppose if this is L again, and now this is L. So now you have the reverse inequality here, because now your L is now equal to x1 minus x2, and that is greater than or equal to x1 minus x2. Right? And so both these inequalities cannot be true simultaneously if they are strict inequalities. So so the implication of this is that your x1 minus x2 is equal to x1 minus x2. Right? So here actually, I mean, here these x1 and x2, they are the same points. Okay, so here actually when I am drawing this curve, I am considering this particular curve which is going to this particular straight line here. Okay, so this x1 and x2 and this x1 and x2 that I am considering, these are the same two x1 and x2 here. So that is why I mean both these inequalities are actually referring to the same x1 and x2 and x1 and x2, and so both of these cannot simultaneously be true if they are strict inequalities. Hence you have to have equality in this case, and so that shows that the distance between any 2 points is preserved because the x1 and x2 that we had chosen were completely arbitrary. So that completes the proof of this particular theorem. So so basically, to summarize this, this gives a very nice physical interpretation for the entire strain tensor. So what we have shown is that if you have a rigid motion, then the strain vanishes, and if the strain vanishes, the motion has to be rigid. So this statement that if the motion is rigid, then the strain being 0 is not very surprising. That is quite intuitive. But the converse statement that if the strain is 0, then the motion is rigid is not so intuitive. But that is what we have basically shown. And so, as I said, that actually this is a very nice result which is valid for any strain measure actually. So we have already given the relation that E and E bar are linked as E is equal to this F transpose E bar times F, right? So if E is equal to 0, then we see that E bar is also equal to 0, and if E bar is equal to 0, then E is equal to 0. So actually, if the motion is rigid, then E bar is also 0, and if E bar is 0, then the motion is rigid. So so basically this is a property of any valid strain measure, that if the motion is rigid, then that valid strain measure has to vanish. Okay, so now let us look at whether the linear strain approximation vanishes if the motion is rigid. Okay, so that's and we will see that it does not, because we have arbitrarily dropped the nonlinear term in getting the linear approximation, right? So let us look at that. So what we have seen so far is that if the motion is rigid, for rigid motion, so for rigid motion, we have seen that F is equal to Q of T belongs to R plus, correct? And then if you now write a displacement gradient from this, so del U is equal to F minus identity is equal to Q minus identity, right? And so your epsilon is equal to half of del U plus del U transpose is equal to half of Q plus Q transpose minus 2 times identity, which is not equal to 0. Okay? So you can see that actually if you have a rigid motion, then the linearized strain tensor does not vanish. Okay, which is not surprising, because as I said that actually there is this del U transpose del U, correct, term actually in the nonlinear strain, which we have arbitrarily dropped, right, as an approximation. And so so the linearized strain tensor is not a valid strain measure, but it's a good approximation to be used for engineering purposes, right? So see, nonlinearities are always very difficult to deal with, and so if we can use a linear approximation, right, which is valid, as I said, that when the displacement gradients are small in some norm sense, then we should we can always simplify things, and so in that sense you can use this as an approximation when the gradients of the displacements are small in some norm sense. But otherwise, strictly from a mathematical viewpoint, the epsilon is not a valid strain measure, because as we have shown that it does not vanish even if the motion is rigid. So then actually one can ask the question that when does the strain vanish, right? So that question we will look at a later stage, but here I will just try to indicate the answer, that here if U is equal to W of T times capital X plus C of T, then this strain measure will vanish. So that means then in that case you will get that del U is equal to W of T belonging to Q. And then you will get that epsilon is equal to 0. Okay, so if your U is of this particular form with W of T belonging to Q, then in that particular case you will see that the linearized strain tensor vanishes, and also the converse is also true. So all those things will prove at a later stage that if epsilon is equal to 0, then U has to be of this particular form here. So anyway, so those statements, as I said, that we will look at those statements at a later stage. But right now, let us now go back to our original agenda, which is trying to show what are the relations between length, area, and volume elements. Right. So right now we have completed the length element. Right. So we have the length element helped us define a strain measure. So now let us look at the area elements. How area elements transform under a deformation. So area transformation now. Area transformation. Yes. So let us look at that. So so this is basically now some area here, and then this is your dA ds0, and then that is going to some element of area ds, let's call it. So suppose if this is the normal n0, then it is going to some normal n. This is your ds here. So So this is the normal to at a point on the surface of the undeformed configuration, and this is the normal unit normal in the deformed configuration. So we will see how these two are related under a deformation also. So first we will define what is known as the Euler transform. Okay, so so first, before that, let us define. So if T now is a tensor field defined over the reference configuration, defined over the reference configuration. Then we can write del x dot t is del Tij by del xj. So the I component of this can be defined in this particular way here. Right, and then similarly, if tau is a tensor defined on the deformed configuration, so if tau is a tensor field on the deformed configuration, then the divergence del dot tau is equal to, so again the ith component is equal to del tau ij by del xj. Right, so this is so this is a tensor field over the reference configuration, and this is over a deformed configuration. And as usual, whenever I am writing these component forms, they are with respect to a Cartesian basis. Okay, so not with respect to some curvilinear basis and so on. So here all these initial notation formulae are with respect to a Cartesian basis. You can write the divergence theorem for this. So this is del x dot t dv0 over v0 will be equal to t times n0 times ds0 over s0. So this is over the reference configuration, and then similarly we can write the divergence theorem del x dot tau times dv. So this is over the deformed configuration. This is tau times n times ds over s. Okay, so this is over v of t. This is v of t. Yes. Okay, so now let us define the Euler transform now. Euler transform. So we define that as T of x is defined as tau of x times cofactor of x. This f is the deformation gradient. So actually this x itself is chi of x comma t. So if you substitute x is equal to chi of x comma t, this whole thing is a function of x, and so that I am writing as this t of x here. Okay, so this let us now find a relation between the divergences of these two things here, right? So theorem now. Let t be as in start. Okay, so t of x. So if we define our t of x as in star, then del x dot t is equal to j times del x dot tau. So this is the relation between the divergences of t that is defined on the reference configuration and this tau that is defined on the deformed configuration here. And the relation between the normals, this is n0 ds0 is equal to tau of x times n times ds. So this is another relation that we will show, and then using these relations we will show that ds is equal to cofactor of f times n naught, the norm times ds naught, and then final relation that we will show is that n is equal to cofactor f times n naught divided by the norm of cofactor f n naught. Yes, so this is the relation between the unit normals here. Right, so, okay, so now let us try to prove this particular theorem here. So first we will prove what is known as the Piola identity. So proof, so just try to write it here. So proof. So first we will prove the Piola identity. So that says that del x dot cofactor f is equal to 0. Right? So this is not a very intuitively obvious relation, but we will show this first and then use this Piola identity to find the relation between the divergences. So that means this particular relation here. Fine. So let us start with the expression for the cofactor. So cofactor Fij is half of epsilon Imn epsilon jpq fmp fnq. Right, and so this I can write as half of epsilon Imn epsilon jpq. Let me write it in terms of the chi map, del chi m by del xp del chi n by del xq. So if I take now the divergence of this, so this is del of cofactor f ij by del xj. Okay, so let me write that. Just write it here now. Just make some room here. Yes, so let me write this expression here. So del of cofactor f ij by del xj is equal to half of epsilon Imn epsilon jpq times del square chi n by del xj del xp del chi n by del xq plus del chi m by del xp del square chi n by del xj del xq. Let's write it in this particular way here. So all I have done is just differentiated this, right? So just it's a product. So the epsilons are constants with respect to the capital X, so they come outside of the differentiation sign, and then the remaining objects I am just differentiating with respect to capital X using the product rule. So this is the expression that I get. Now this I can write as equal to half of epsilon Imn, and the jpq I will take inside, so that is epsilon jpq, then del square chi, so sorry, this should have been m, so just correct that, this should del square chi m by del x j del x p del xj, then this is del chi n by del xq plus epsilon q p q p j del chi m by del xp del square chi n by del xq del xj. Okay. So all I've done is I've just taken this inside and just rearrange the indices using the permutation property, that epsilon ijk is epsilon jki and so on. So that permutation property. So instead of epsilon jpq, I have written it as q qpj. So yes. So let me just see. J, yeah. Okay, actually, maybe I'll just keep this as QJP. Sorry about this. So this should have been QJP. Yeah, this should have been QJP. Yeah. Okay. So yeah. So all I've done is just change the indices here, and now you will see that this P and this J, okay, and this P and this J, okay, they are occurring here. So what you can do for this first term here is that you can rename P as J and you can rename J as P. Okay? And here for this particular term, you can see that this Q and J are also occurring in this one here, and so you can rename the Q as J and the J as Q. So because these are all dummy indices, so here I will rename Q as J and J as Q. Okay. And then you will play the usual trick that basically del square chi m by del xp del xj is equal to del square chi m by del xj del xp. Okay, so that order of differentiation can be interchanged, and epsilon, so now this will go to, because I have renamed it, this will go to epsilon of, so j is called as p and p is called as j, so this will go to this, right? But this is equal to minus of epsilon jpp, right? And so you will see that this whole object, right, and similar thing can be done even here also. So your qjp will be minus of epsilon jqp, and so basically what will happen is that this whole object is equal to minus of this same object here, and so this whole object has to be equal to 0. So what we have shown is that this del of cofactor fij by del xj is equal to 0. Okay, so this so basically it is just a manipulation of this indices on the alternate tensor, and that is how you get it. So finally what you will get, is that del of cofactor f ij by del xj is equal to 0. So we have shown this pure identity. Okay, now using the pure identity, we will prove the relation between the divergences of the tensors that are defined on the reference configuration and on the deformed configuration, right? The t and the tau, whatever we had written earlier. So let us look at that now. Yes. So let us do that. So del x dot t. So we have seen that t of x is equal to tau of x times cofactor of f. Correct. So now the del dot t I can write as del x dot tau of cofactor of f. Correct. And then this I can write as, so let me switch to indicial notation. So let me write this as the ith component. Similarly, let me write the ith component of this. So this is del tau IR by del xj times cofactor of f times r of j. Okay, so here actually you would also get a term with the derivative of del of cofactor f r j with respect to j, but that is equal to 0 because of the pure identity. And so effectively, this cofactor f is like a constant tensor when you are differentiating with respect to capital X. And so that is why there is no differentiation sign on the cofactor of f. After this, it is just a matter of using the chain rule. So now this I can write as del tau IR by del x m times del chi m by del xj times cofactor of f times rj. And this object here is nothing but f and j. And so this is nothing but f times cofactor f transpose of mr. So this is equal to del tau IR by del xm times this is f times cofactor of f transpose, right? So this is or let me just write it as yes times. So this is m r component, right? And we have seen that f times cofactor f transpose is nothing but determinant of f, right? Times identity tensor. So let me just write it here. Yes, so this I can now write as del tau IR by del xm times determinant of f. So let me just write it as j. Determinant of f is just j times delta mr. So this is just the identity tensor, the mr component of the identity tensor. So that is this, and this I can now write as equal to j times del tau IR by del xr, the substitution operator property of the Kronecker delta. And so this is nothing but the ith component of del dot tau. So this is equal to j times del dot tau the ith component. Okay, so what we have shown is that del dot t is j times del dot tau. So this implies now that del dot t is equal to j del dot tau. But you have to be careful here. This divergence is with respect to the material coordinates, that is capital X. This divergence is with respect to the spatial coordinate, which is small x here in this particular case here. Okay, so we proceed to the next relation now. So let's look at that now. Yes. So let us look at this term t times n0 times ds0 over s0. So this is equal to integral over v0 of del x dot t times dv0. So this in this step I am just using the divergence theorem, so which I had written earlier, right? And now this we have shown that this is equal to del x dot t is j times del dot tau. Correct? So here actually this one is j times del dot tau times dv naught. But j times dv naught we will show in the next step later. So that is equal to dv itself. So this I can write as del dot tau times dv itself, right? And this I can write as integral of tau times n times ds over s. Okay, and then now use the arbitrariness of s naught and s of t to get the following relation. So let me just write that. So we will get now that so from this because of the arbitrariness, so since s naught is arbitrary, what I will get is that t times n naught times b s naught is equal to tau times n times ds. Okay, now this may look a little bit strange, okay, because actually these are over different domains, but if I include the ds naught, then it's not a problem. Okay, so just to maybe give an analogy about why we get this particular relation. So if you look at dx dy, right, we write it as r dr d theta, right? So because this dx dy is r dr d theta, although this may be over a rectangle and then we are transforming it to the corresponding domain in polar coordinates. So what I am indicating is that this relation that we are writing is exactly analogous to this particular relation. So you can put in some more thought to see why this particular step is justified in this case. Yes, then now let us take tau to be identity in this particular relation here. So take tau, now take tau to be equal to the identity tensor. Okay, so we have seen that t is equal to tau times cofactor of f. Right? So what you will get here is that this is equal to cofactor of f. Right? T will be equal to cofactor of f. So here, because tau is identity, so you will get that n times ds is equal to now cofactor of f times n naught times ds naught. Okay, so this is now the relation that you get between n ds and n naught ds naught. Okay. Now take the norm on both sides. Take the norm. So take the norm on both sides. So what you will get is that ds. So because n dot n is equal to 1, okay, n dot n, because the normals are always unit normals that we are considering here. So we will get, after taking the norm and noting that n dot n is equal to 1, so this you will get as the norm of cofactor f times n naught times ds naught. So this gives a relation between the area elements now. And then now just substitute this ds is equal to cofactor f norm ds naught into this particular relation. So then you will get, so from these two relations, then it will follow that n will be equal to cofactor of f times n naught divided by norm of cofactor f times n naught. So that's the relation between the unit normals in the deformed and the undeformed configuration. So if I just draw that picture here again, just to clarify these things here. Here, suppose if I take this, and then this is your n naught, and this is your ds naught. Now it goes into a deformed configuration, and now this is your ds, which is equal to cofactor f times n naught ds naught. Okay, and then the normal, this is your n, that is equal to cofactor f times n naught divided by norm of cofactor f times n naught. So we can see that this is the relation between the unit normals at a given point. Okay, so this point is corresponding to this point in the deformed configuration, and then this is how the unit normals are related. Okay. So now the last thing for today is the volume element. So this basically completes the area element relations. Now let us look at the volume element relations also. So as I said, then that will complete this particular. So we are considering length elements, then the area elements which we just considered, and now the last thing is the volume elements. Now, so let us look at volume elements. Volume element. So actually we have already used this relation, but right now we'll prove this particular relation here. So what we want to show is that dV is J times dV naught. So if you have again this reference configuration, and if you take an element of volume now, dV naught, and then that goes into an element of volume dV, then dV is linked to dV naught through this particular relation, J times dV naught. I mean, again, so you can see the analogy. So you can think like dx dy, right, is equal to, we write r dr d theta, right? So this r is exactly like the J, and so I mean, just to draw an analogy between what you already know and this particular result here. So here this so let us write this volume element as dx1 comma dx2 comma dx3, right? So this is the scalar triple product. So this is your dv actually, and we will take the norm sign, the absolute sign around this. So this is f times dx1 comma f times dx2 comma f times dx3, the scalar triple product. So again, you will get the relation using the fact that dx is equal to f times dx. So I am just using that particular relation here. So remember that this is all happening at a given point, right? So this deformation gradient is at this given point which we are considering here. So this can be written now as E equal to determinant of f. So again with the absolute sign times dx1 comma dx2 comma dx3. So this is again the definition of the determinant. If you recall, this was how we had defined the determinant. So let me go back. I think determinant of t, scalar triple product of x, y, z was equal to tx, ty, tz, right? So this is how we had defined the determinant. So we are just using that particular definition here. And this is nothing but dV naught, and this is nothing but j. So this is equal to j times dV naught. We don't need now the absolute sign because we have assumed that determinant f is greater than 0, right? The j is greater than 0 by the orientation preserving condition. So since j is greater than 0 by the orientation preserving condition. Orientation preserving condition. Right? Yes. So we have used this relation previously, but we had not proved it. But now we have shown basically that dV is equal to j times dV naught with j greater than 0. So this is okay, and then the last thing is that a motion which is volume preserving is said to be isochoric. So we will just define this terminology. So if j is 1, then that motion is called as isochoric. So if a volume preserving deformation, a volume preserving deformation. So that means j equal to 1 is called isochoric. So do not confuse between an incompressible material and an isochoric motion. Okay. So even if the material is compressible, it can undergo an isochoric motion. So let me just give an example. Suppose if you take this square block, right, and then it undergoes a deformation like this. Okay, just the top surface remains at the same height, and then this angle is same, gamma is same. Okay, so this is, you can see that this is a volume preserving deformation, but the material could be incompressible or compressible. So this, when we say this isochoric, that is a property of the motion itself. So it has nothing to do. So even a compressible material can undergo an isochoric motion. Okay, But when you talk, so later on when we define an incompressible material is one that is capable of undergoing only isomeric motions, right? So you cannot have a non-isomeric motion in an incompressible, because that is the definition, that it can undergo only isomeric motions. Okay, so don't confuse between these two different concepts of a motion. So this is a property of the motion. When we say incompressible material, that is a property of the material itself. So that is like a constraint that we are putting that. So typically we will say that fluids are incompressible, right? So anyway, we'll come to those points at a later stage. So we will stop at this stage.